Hey everyone, I hope you're doing well today. In this video, we're going to go over some practice problems dealing with powers or exponents and bases, and then a little bit later, after I think about maybe 10 to 12 practice problems with these exponents, we'll do some practice problems with order of operations. All right, so let's get right into it. For this first example, let's see if we have a power that looks like this, 1.2 raised to the second power. So if you have parentheses, great. If you don't have parentheses, not a huge deal. But let's just identify what the base and what the exponent are here. So right here we see this 1.2. That's going to be the base. So I'm going to write that here. I'm going to say the base here is equal to 1.2. That's always what that's going to be. And then up top here, this 2, this is going to be the exponent. So I'm going to write the exponent is equal to 2. All right, so just identifying the different parts of this expression. So this power has two pieces there. All right, so that's the first question. For this next question, let's take a look and try this where we have an expression. Let me write this one out. It's going to be 7 times 7 times 7 times 7. And so we're going to take a look at this expression and maybe try to write it as a power instead. All right, so instead of writing it 7 times 7 times 7 times 7, we can just write 7 to the 4th power. That's a little shortcut way of writing it, right? And so if we were going to identify the exponent here, this 4 is saying you have 1, 2, 3, 4 of these 7s. So we can go ahead and say that this exponent, let me go ahead and just use this to save a little bit of time here. The exponent here is going to equal 2. 4. The exponent was 2 for the last problem. Okay. Here's another one. Let's go ahead and try saying, what if we have like a decimal? And for decimals, typically we like to write them in parentheses. So what if we have like 0.5 times 0.5 times 0.5? So what is that equal to? Well, maybe we can write this as a power as well. So how many of these do we have? We have 1, we have 2, we have 3 of them, okay? So how can we write this? We can write this as 0.5 raised to the 3rd power, right? So we had 3 of these. So if I said, or we were trying to practice identifying the exponent here was going to be 3. The base would be 0.5, so like the base in the last one was 7, and the base here is 0.5. But if we're just talking about the exponent here is going to be 3. Okay. For a 4th example, let's take a look at looking at a power. So let's try, let's go ahead and try this 1/7 in parentheses. Again, we typically like writing fractions inside parentheses, so we know that the exponent belongs to the whole thing and not just to the numerator. And so maybe let's try to write the power as a multiplication sentence. So it's not very long, it's just 1/7 times 1/7, right? Just make sure you don't write 1/7 times 2, okay? And so what is this equal to? Well, in the numerator, 1 times 1 is going to be 1, and in the denominator, 7 times 7 is 49. So if we had to evaluate this or solve the power, this is what it's equal to. It's equal to 1/49. For a 5th example, let's take a look at this one. Let's have another power, just like the last example. Let's write 1/4. And the base here is less than 1, so we should get a smaller number. So we're going to write this out as 1/4 times 1/4 times 1/4. Okay? In the numerator, 1 times 1 times 1 is 1. And in the denominator, 4 times 4, let's go ahead and write this out. This is 4 times 4, that's going to be 16. And then 16 times 4 is going to be 64. So I'm going to go ahead and write that right like that. Okay? For a 6th example, let's see. Let's try something like this. We have, let's do 1 5/10 or 1.5, and let's multiply that by 10 to the 4th power. Okay, so if we're going to go ahead and multiply these, what can we do? So let's start with this power here. So based on powers, we should go ahead and deal with this one over here to the right. So what is that? 10 to the 4th power. I can go ahead and just write that on the side here. That's going to be 10 times 10 times 10 times 10. So 10 times 10 is 100, times 10 is 1,000, times 10 is 10,000. So this is really equal to 1.5 times 10,000. Okay, and then if we go ahead and multiply that out, you could just slide the decimal 4 times to the right if you'd like, but you could also use a calculator if that helps, if you're not sure, and that's going to be 15,000. Okay, so there are those 6 problems right over there so far. And let's see what else we can try here. Let's try a 7th example here. I guess I can move down, right? Yeah, I got plenty of space here. So 7. So for this next one, try to listen to the scenario here. So someone's driving their car and they record how many miles they're driving each month, and they're going to record their distances for 2 months. So for month 1, this person's going to drive 5 to the 4th power number of miles. And then for month number 2, let me go ahead and write that. Month number 2, they're driving for 4 to the 5th power number of miles. The question you're asking here, or I'm asking is how many miles does this person drive for both of these months combined? Okay, so you can't just add these up just like this. We got to try to remember what this represents. So 5 to the 4th power, this equals 5 times 5 times 5 times 5. Okay, and if you take a look at this 4 to the 5th power, that's really 4 times 4 times 4 times 4 times 4. There's going to be 5 of those here. So 5 times 5, that's 25, times 5 is going to be 125 times 5. I think that's going to be 625 miles for the first one, equals 625 miles. Okay, and then for this next one, let's try to see if we can multiply this out. And again, feel free to use a calculator if you need to. But I think this 4 times 4 is 16. 16 times 4 is 64. 64 times 4 is 256. 256 times 4, I think that's 1,024, if I'm not mistaken. 1,024. I don't want to write something wrong, but I think that's right. Yeah, I'm pretty sure that's right. Okay, so if we're going to find the total here, so if we add up the month 1 plus the month 2, then this total is going to be 1,649 miles. That should be correct. Okay, so 1,649. So make sure you evaluate those powers first individually. So 5 to the 4th power, then 4 to the 5th power, and then add those two amounts together. That's the total amount this person drove their car for these 2 months. Okay, let's try an 8th one here. For an 8th example, let's take a look at the number 27. And let's say, how can we represent 27 using a 3? Okay, so let's try to think about this. If we have 3, so if I have 27, so how can we write an expression so that we can get to 27 using the number 3? Well, that's kind of an interesting idea here. So let's go ahead and say, okay, this is well, 27 doesn't equal 3, but what if we multiply it by another 3? Because we're dealing with exponents after all, and powers and repeated multiplication. So 3 times 3 is 9. That's not 27 either. What if I multiply by another 3? So 9 times 3, that is 27. So how can we rewrite this? Well, we can say that 27 is equal to 3 to the 3rd power. So that's how you could write 27 by just using 3's. Okay, it's really 3 times 3 times 3, or 3 to the 3rd power. Okay. Here's a 9th practice problem or idea to take a look at here. So let's say the area, so we have the Great Lakes. Okay, so the Great Lakes, and let's see the area of the Great Lakes is going to be, let's write the area equals 9.5 times 10 to the 4th power square miles, or miles squared. Okay, so how many square miles is the area of the Great Lakes? So this might be a little bit harder to understand when it's written like this. This is called scientific notation. You'll learn more about it in Algebra 1 and in science classes. But what you do is, again, like we did earlier in number 6, we're going to evaluate this first. So we're going to take this 9.5 and multiply it by this 10 to the 4th power, which I think we already know from earlier that 10 to the 4th power is right over here. I think we said that was going to be 10,000, right? So that's going to be 10,000, just like that. And so if we multiply 9.5 times 10,000, that's just going to end up equaling 95,000 square miles. Okay, that would be the area of this. So if you're wondering what 95,000 square miles, like what it actually is, just try to imagine you have like a square that's 1 mile by 1 mile. 1 mile by 1 mile. So that's a very big square, right? And imagine there's 95,000 of those square miles. So that's quite a large area to cover. Okay. Let's try another. Let's move on down here. Number 10. Let's say number 10. Let's say, so humans can distinguish up to 18. Let me write this out. Humans can distinguish up to 18,400,000 individual dots, pixels, right? Humans can identify this many pixels based on like what they can see on a typical screen. Okay, so the question is can humans or people see or distinguish pixels on a TV that has two, let's say the TV, let's see this HD, let's call it HD TV, and that's going to be 2 times 10 to the 6th power pixels. So imagine a TV shows that many of them, right? So let's see if we can compare these two values. So 18,400,000, that's a lot of pixels. So can a human actually distinguish the pixels on an HD TV that has this many pixels? Well, let's go ahead and see. It's hard to compare these right now, but we know 10 to the 6th power, we know that's going to be 10 times 10 times 10 times 10. That's 4 of them, that's 5 of them, that's 6 of them. So that's 10 times 10 is 100, that's 1,000, that's 10,000, that's 100,000, and that's what, a million, right? That's a million. So this is going to equal 2 times a million. So that's 6 zeros. And so that's equal to 2 million pixels. That's what's going to be on the TV, right? So the question is can a human answer that? Or not answer that, can a human see that? And the answer is going to be yes, because if we think about it here, this 2 million pixels that's on the TV, well, if the human eye can see this many pixels, then 2 million is less than that, right? So because we know that this 2 million is less than, it's a good idea to use comparison here, is less than this 18,400,000, then the answer is going to be yes. Yes, a human can. Okay, so that's the answer to that, because it's definitely more pixels that the human could see compared to how many are on the TV. Okay, let's take a look and see another practice problem. So I'll go up here, maybe. Number 11. So let's say that you put $1 into maybe a bank account. Let's go ahead and put that $1, and you put it into an account, and then every 8 years, let's go ahead and write this down. So every 8 years, let's say that your money is going to double. That's pretty cool, right? So if you leave your money at home or whatever, it's not doing anything. But if you go ahead and put it into this account, they're telling you that every 8 years it's going to double. So maybe that's not a big deal now, but maybe it'll turn into something else. So let's see, if we have this expression of like 1, and then we have times 2, and let's say that we do this a few more times. 4, 5, let's do it 6 times here, okay? So I'm wondering if this multiplication sentence represents how much money there will be in 48 years. So let's go ahead and write that down. In 48 years, is this going to represent how much money's in there? That's the question. So it's a yes or no question, right? And so let's see. If you have $1, that hopefully makes sense here, that $1 gets put in, and in 8 years later, it's going to double. So that's in 8 years, right? And then another 8 years later, which is 16 years, it's going to double. And then another 8 years go by, that's 24 years, that's going to double. What if another 8 years goes by? That would be, I think, 32, and it's going to double. Another 8 years go by, that's going to be 40 years later, that's going to double. And another 8 years later, that's 48, that's going to double. So hopefully we can see and identify if this actually makes sense or not, but you have your dollar in there. it doubles once, it doubles again, doubles in 24 years, doubles in 32, 40, and 48. So I think this does make sense, right? And we can verify this if we multiply this out, if this actually works. But you could also take a look at this 48, the 48 total years, and if we know it's going to double every 8 years, we can see how many 2's there are here, right? So if we see there's 1, 2, 3, 4, 5, 6 2's, that means it doubled 6 times. So if we take this 48 and we divide it by the every 8 years that we knew, right? Then that is actually equal to the 6 2's. So the 6 2's gets us there, okay? So we could go ahead and write that out as like 1 times 2 to the 6th power if we wanted to. Or we can say that this is also going to be 1 times, what is 2 to the 6th power? Well, let's see. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, times 2 is 64. So $1 is going to turn into $64. If you just leave that $1 there, that's pretty cool. In 48 years, why not have $1 turn into $64? So because it's doubling 6 times, we know that this is correct. So if the answer is this representing what's happening, this expression, the answer here would be yes. Okay, this does work. And hopefully the explanation I kind of gave and what I drew shows that I understand that. And so hopefully you can draw that or write that yourself and you can verify that that makes sense. All right, number 12 here. Number 12, let's see if we have the number 343. And let's say that we have some options here. So let's say option 1, for option 1 we have 8 to the 3rd power. For option 2, we see that we have 6 times 6 times 6. Option 3, let's say we have 7 to the 3rd power. And then we have option 4, let's say we have 7 times 7 times 7 times 7. And my question here is, let's try to see maybe which one of these expressions equals 343, right? So 343, we can try each of these out if we'd like to. So maybe we can do that just to verify. So 8 to the 3rd power, that's 8 times 8 times 8. So let's think about what that is. So 8 times 8 is going to be 64. And 64 times 8, that's going to be 512, right? So that's not the answer, okay? This next one is going to be 6 times 6 times 6. So 6 times 6 is 36, and 36 times 6, that's going to equal to, whoops, I think I wanted to write that using this. That's equal to 216, so that's not equal to 343. And then for this next one, well, if this one's not right, then it has to be the last one, right? So 7 times 7 times 7. So 7 times 7 is 49. 49 times 7 is going to be 343. So I think we found our answer there. So that would be the correct one. And this last one is too many 7's. So that would be actually 343 times 7, which I think is going to be 2,401. Okay, so I think we know our answer for this one. We're just testing to see which one of these equals 343. Okay, so there you have 12 practice problems just dealing with powers, and hopefully you feel a little bit more comfortable with them. All right, so let's go ahead and try some order of operations now, and we'll include our exponents in now that we know our powers a little bit better. So for this first example, let's do the quantity of this 14.7 plus 9.3. And let's go ahead and multiply that by this fraction of 1/2 raised to the 2nd power. All right, so order of operations states we got to follow the exponents after the grouping symbols, right? So we're not going to do the exponents first, even though you might feel like you've just been practicing a lot of them. But we have this grouping symbol over here. And so we're going to start with that. So 14.7 plus 9.3. Hopefully you can do that by hand, but if you need a calculator, go ahead and use one. So we have 24 times, and then we're going to just copy this. Now, this parentheses, obviously it looks like parentheses because it is, but it doesn't mean a grouping symbol because there's only one thing inside of it, right? So it's not actually a grouping symbol, it's just 1/2 to the 2nd power. Okay, it's just to let us know that the whole fraction's being squared. So this 1/2 squared, really just on the side, if that helps at all, just because we're practicing exponents a little more right now, that's 1/2 times 1/2. So 1 times 1 is 1, 2 times 2 is 4. So this is really just 24 times this 1/4. And on the side, again, if you need to see this, 24 is 24 over 1 when you're multiplying fractions. You have to write them both as a numerator and denominator. You can cross cancel. Hopefully that rings a bell. And that would be equal to 6 over 1 or just equal to 6. So 24 times 1/4 is equal to 6. Or 24 divided by 4. It's the same thing. Okay. Let's try another practice problem here where we have to evaluate a numerical expression. That's what these are. Except let's not use any fractions or decimals this time. So we have 3 things to do. Which one goes first? Well, there's no grouping symbol, so I think the exponent goes first here. So 5 to the 2nd power, that should be 25. So 25 minus 9 divided by 3. And then we should divide next, I think, right? Division's more important, so it's 25 minus 9 divided by 3 is 3. And then finally, 25 minus 3 is equal to 22. So that would be the value of this expression. Okay, let's try another one. For a third example, let's try a little longer one here. And let's do 4 to the 2nd power divided by, we'll do the quantity of, remember when we say what's inside, it's the quantity of 3.2 times 2. I'm not a fan of using multiplication with decimals like that, but I think that'll be okay. We don't have variables, so I'd be okay using an x for multiplication here as well, I think. But once there's variables, it gets a little bit dicey. Okay, so okay, we have brackets and we have parentheses, so we always work our way out. So we have to start here. So I'm going to copy literally everything else. Like don't even think about it, just copy. 3.2 times 2, that should be 6.4. Since it's only one number now, you don't need to write the parentheses. Okay, so now we have this inside brackets, so that's the next thing we have to do. We got to work our way out. And so we have 4 squared on the outside, just kind of hanging out, not knowing what to do. 6.4 plus the 1.6, I think that's just 8, right? That's just 8. And now it's finally no more grouping symbols. Again, once you have one number inside, you don't need to write it anymore. So 4 to the 2nd power, that's 4 times 4, so that's going to be 16. 16 divided by 8, that's going to be just 2. All right, just like that. So there's a third example. Let's try another one. This one's a little bit trickier. Let's try this one where we have to say we have a target value. Target. Some people say target. Target value is going to be what? 23 here. Okay, so I'm going to give you an expression, and let's see if we can make it equal to 23. So let's do 5 to the 2nd power minus 0.2, or 2/10, and then let's multiply that by 8 plus 12, and then multiply that by 1/2. So if you were to solve this thing right now, just following the order of operations, the way it's written, this would be 25 minus 0.2 times 8 plus 12 times 1/2. But the next thing we're going to do after that is we'd have to do multiplication. So 0.2 times 8, just think about what's 2 times 8, and that's going to be 16, but it has one decimal place, so it's going to be 1.6 plus 12 times 1/2. The next thing we do is multiply 12 times 1/2, or half of 12. That's 25 minus 1.6 plus 6. Okay. Then what's 25 minus 1.6? That's 23.4. So 23.4 plus 6. And if you add those up, that would be 29.4, which clearly isn't equal to this 23 that it's supposed to be equal to. So I'm saying, where can we put parentheses into this problem so that we do get 23, right? And so something I'm looking at is like this decimal here. This decimal seems to be a bit of an issue because if you multiply by decimal, likely it's going to be another decimal. But decimals work by powers of 10, right? So like tenths, hundredths, thousandths. And so what I'm thinking here is, why don't we put the parentheses around here? See what happens if you enter parentheses right here, right? So if you do this 8 plus 12, that would have to go first, right? So that would be 5 squared minus 0.2 times, what's 8 plus 12? That's going to be 20. And then we still have to multiply this by half over here. And then now that we did parentheses, what would we do next? Well, we would go ahead and we would do this 5 squared. That's going to be 25 minus 0.2 times 20 times 1/2. And the next thing we would do here is multiply this 0.2 times this 20. So what's 0.2 times 20? Well, 2 times 20 is going to be 40, but move the decimal over, so that's going to be 4 times 1/2. And then what is 4 times 1/2, because multiplication goes next? 25 minus, well, 4 times 1/2 is going to be 2. And then 25 minus 2 is going to be 23. So we did it. It does equal this target value of 23. All right, cool. So there's a few different practice problems already on some of these order of operations, and they're just slightly different levels of difficulty and styles. Hopefully it's making sense, though, how we can use the order of operations, and we should be following the same order to get the same solutions here. So 4 was a cool problem because we were all trying to make the value 23. So you can put parentheses in different locations to get different values, but that's the one place we can definitely put parentheses to get 23. All right. So here is a 5th example. Let's say someone has a rectangle in their backyard, and we have to play around with some dimensions of it. So here is a rough sketch of a rectangle, and I'm going to tell you that the length is going to be 27 feet. So I'm going to put maybe 27 right over here. I'm going to say that's equal to the length. And then I'm going to say the width. The width is going to be 1/3 of the length plus 4 feet. So the width here is going to be on the side. And I'm saying the width is going to be 1/3 of the length. So 1/3 of the length, that's 1/3 times 27. And then it says, we'll say plus 4. Okay, so the length is 27, and the width is 1/3 of the length. And we know the length is 27, so 1/3 of, that's multiplication, and then it's 4 more than that. So what if we have to find the area of this whole thing? Well, how do you find the area of a rectangle? Well, area, we know, is length times width for rectangles, right? So what's the length? Well, we know the length and we know the width. So let's go ahead and write this in. The area is equal to the length, which is 27, multiplied by the width, but the whole width here is 1/3 times 27 plus 4. That's the entire width. Okay, and so if we solve this, we will get the area of this rectangle. So where would we have to start? Well, following the order of operations, we have to go inside the parentheses. Inside, though, whoopsies, inside we have to start with here. So what's 1/3 of 27? Well, 27 divided by 3 is 9, so that's going to be 9 plus 4. Again, if you need to multiply that out on the side, that's totally okay. If you do 1/3 times 27, you'll see that these cross cancel, and you do get 9. But again, I'm assuming you can use a calculator, or you can do this on your own and do the scratch work. So all the calculations, do it on the side on your own, but this is what you should get. Okay, so I'm not going to write it every single time, but I hope that's something you can do on your own at this point. Next, we're going to add 9 plus 4 because that's in the parentheses. 9 plus 4 is 13. And then so finally, we have 27 times 13. That's just a little bit of standard algorithm. I think it's 270 plus another. I think it's going to be 351. Okay. And let's say each side was like measured in feet. So this would be feet squared for the units. Okay, so if the length was 27 and the width was 1/3 of that plus 4, we found out the width eventually was 13. So I can also write that down on the side here, but they told us the length was 27. Let's say that's feet. But the width, we had to do a little bit of work for it. They said it was 1/3 of that, which was 9 plus 4 is 13. So the width was 13 feet while the length was 27 feet. So once we found those out, we were able to find the area of this rectangle. All right. All right, for this next one, let's say that basketball team scores game number 1 a certain number of points. We'll do 3 games here, game 1, game 2, game 3, and say they score 38 points in the first game. And then for game 2 and game 3, we don't know how many points were scored in each one specifically, but we do know how many points they scored in total for game 2 and game 3. So whatever this number is for how many points and how many points, we don't know, but combined, let's say it's going to be 77 points, okay? So for every point scored, let's say that they're going to earn some money, okay? So turns out they're going to get 50 cents per point. I'm going to go ahead and write that down. 50 cents per point scored. So the question is well, it doesn't matter what they got in game 2 and game 3 as long as we know they got 77 total points in those 2 games. But the question is can we write a math problem or math expression or sentence that tells us how much money that they're going to be getting? So let's see, if we write down this expression of, let's say, 38 plus 77 times the 50 cents, the question is does this equal how much total money that they're going to get? So I'm going to say, does this equal the total money? That's kind of the question here, right? And so if you were to solve this expression, you could think like, will this equal the total amount of money they make? And let's see, if we do the order of operations for those 77 points, if they make 50 cents for each one, then that means that, okay, we have 38 here plus 77 times 50 cents, that's going to be $38.50. And then if you add that on to this 38, then that should equal $76.50. So the question is does that equal the total amount of money they would make? That's kind of the idea here, right? And so if you think about it, I don't think this makes sense here, right? Because it makes dollars and cents. It actually doesn't make sense here because why would they take this $38? This is 38 points they got earlier. They don't get $38 for those 38, points they got, right? They're supposed to get 50 cents for each of those. So I think that this expression is incorrect. And so what can we do to fix it, right? So let's go ahead and change this expression around a little bit. What if we insert parentheses or brackets like right over here? Right? They're supposed to be getting 50 cents for every point. And so what's the total points they scored? Well, I think if we go ahead and add these together, won't that be the total number of points? So it's 38 plus the 77. That should be 115 total points. And then we should multiply that by 50 cents per each of them. So if we do 115 times 0.5, or 50 cents for each one of those, you can again use standard algorithm or use a calculator, and that should end up being $57.50. So I do believe this would equal the total money that they would make based on getting 50 cents for each of them. So if you think about it, the original expression just kind of had this 38 plus 77 times 0.5, right? But that doesn't get us the correct answer. So what we have to do is we had to put parentheses in here to say, okay, let's put the parentheses in so we have to add first, then multiply, instead of multiplying, then adding. And that'll get us the correct value that we're looking for to represent the situation. Okay? All right, so for this next example, let's say that we have someone buying a new computer, and the new computer has a total cost of, let's say, $800. Okay? We know that someone's going to put down, they're going to pay initially, say put down, so that's kind of like an initial payment, and so you're going to pay $120 first. Let's say that we're going to be getting a discount, maybe it's a student discount, right, of $50. And then let's say this person gets some help for a birthday, and for the gift, this person's parents are going to say, okay, they're going to pay half of what's left. Okay, so happy birthday, have a gift of whatever the balance is going to be after all of that. So The question is how much does this person still have to pay for the computer? So let's see what this expression would look like. Well, whoopsies. Let's see, the whole total cost of the computer was $800, right? And let's see, if that was a total cost, but she already paid for some of it, what did she already pay for? Well, she paid $120. She already put that down, and that means that she paid for that amount. And she also got a discount of $50. So that's another thing she's already paid. So we're going to add together what she's already paid and subtract it from the total cost. And then her mom's going to help her out with half of it, or her parents or whatever, for her birthday. All right, so hopefully this makes sense of what she's still going to have to owe, or this person's still going to pay afterwards, right? So let's see. Let's going to add this up first, because that's going to be the total that she's already paid or doesn't have to pay, right? So 800 minus, that's $170 that she already paid, right? She got the discount, and she already just said, I have $120, so I'm going to pay it right now. And so if the total cost was 800, but she already paid that, it makes sense, hopefully, to subtract this. So 800 minus the 170 she's already paid, that's going to be now $630. But remember, for her birthday, they're helping her out, and they're paying for half of what's left. So 630 divided by 2, that's going to equal 315. So this person still owes 315, but their parents are going to help them out with 315. So we're going to say still owes $315 on the laptop. But it's pretty nice because for their birthday, they got basically a $315 gift. So I'm going to write up here just so it's clear. The B-Day gift was also $315. Whoops. The B-Day gift was $315 as well. Okay, so that's a pretty big gift. Okay, so computer was originally $800, paid $120, got a discount of $50, and then they got a $315 gift essentially. So this person's really only paying $315 for the laptop after all of that. Okay. All right, let's go ahead and try another one here. So for an 8th practice problem, let's say that somebody is going to be walking for a whole month. I'm going to write here 1 month of walking. And so how many months are there, or how many weeks are there in a month? There are 4 weeks typically, right, in a month. And so let's say we know that someone's going to be walking, and we're going to go ahead and calculate how much they have walked in total for their miles. So let's say they walk on average of 3.5 miles per hour, okay? And so for 3 weeks, let's say for 3 weeks out of the month, they are going to be walking 6 hours a week, 6 hours per week. And not only that, we're going to say that for 1 week, so that's what they're doing for 3 out of the 4 weeks, but for 1 week, they're going to walk for half of the regular rate for 4 hours. So what's half of the regular rate? Well, her regular rate is going to be this 3.5 miles an hour. That's what she's doing here. So what's half of that? I don't know, but let's go ahead and just write half of the 3.5. The dots are annoying and a little bit hard to see, so I'll use parentheses. That's half of that, but she's also only doing that for how many hours that week? She's doing it for 4 hours instead. So she's walking a little bit less, and she's walking slower for one of those weeks. So 4 hours instead. So the question is what is the total number of miles she walks, or this person is walking? Total miles for the whole month. Okay, so let's see. This person is going to say for weeks 1 through 3. Well, 3 weeks, let's do 3 times. 3 times 6, that makes sense, I think. 3 times 6, because they're walking for, 18 total hours. And then they're also walking 3.5 miles an hour for each of those hours, right? 3.5 miles an hour for each of those hours. So that's going to be for the first 3 weeks. And then what is she doing after that? After that, she's going to be doing 1 week where she's doing half of that rate. So half times this 3.5. And she's doing that for, I think, 4 hours? I don't know if I needed to put all these parentheses, but I guess we could drop one of these. Let's go ahead and drop these ones. It's too many parentheses. It's not wrong by any means, but I think that's a little bit easier to see. So this first one is going to be the first 3 weeks. And then this one over here is going to be representing the 4th week. Okay, so going ahead and solving this, if we say 3 times 6, let's try to see what that represents. That's 18 hours she's walking, and she's going at a rate of 3.5 miles an hour there. Okay, and then how much is the total amount of hours she's doing in the second time, or like the last week? She's doing that for 4 total hours. And we can also take a look and say, okay, she's doing 4 total hours, but what rate is she going at? Well, she's going half of the rate. So what's half of 3.5? Half of 3.5 is going to be, I think, 1.75. So 1.75. So I'm just trying to hopefully like keep this organized. And so this is the number of hours she's walking for. And this is the number of hours she's walking for here. So you can see the consistency, okay? So the hours she's walking, and then over here, what we're looking at, let's see if I can identify this. This is, I don't know, this is fine. This is just the rate she's going at. So this is the rate, how fast she's going. And this is the rate she's going for that last week. Okay, so imagine if you're going 3.5 miles an hour for 1 hour, then you've traveled 3.5 miles. But for 2 hours, then that's double that. That's 7 total miles. And if you do 3 hours, that's triple. So for 18 of them, instead of doing repeated addition, we could do 18 times 3.5. So if we go ahead and multiply like these two together, for the first 3 weeks, she's going to go to a total of 63 miles. And then if you take a look here, if you do, her rate is 1.75 miles an hour. She's walking slower, but she's doing it for 4 hours. Whoops. Then we can go ahead and say 4 times 1.75. I think 2 times that is 3.5. I think it's going to be a total of 7. So she's only doing 7 miles for that last week. And so if you add those two together, that's a total of 70 miles. Total 70 miles. And there we go. And with that, let's just try one final practice problem here. So let's say we have an expression of 102.4 minus the quantity of, in the grouping here, we'll do 2 to the 3rd power times 3, and then plus 13.8. Let's go ahead and close those brackets and then divide this whole thing by 7. And let's say we have a few different expressions that we want to see if they're equal to it. So let's try this 102.4 minus this 3 squared times 3 plus 13.8 divided by 7. And then let's see another option here. Let's do 10 squared plus 2.4 minus the quantity of 37.8 divided by 7. Here's a third one. Third one here is going to be 102.4 minus the quantity of 6 squared plus 1.8 divided by 7. For a fourth choice, let's try 102.4 minus the quantity of this 2 cubed times 3 plus 20.8. And a fifth choice here. Let's try this 60 plus 42.4 minus the quantity of this 8 times 3 plus 13.8 times 7. Okay, so we're going to see which one of these are equivalent to the original expression above. So even just looking at this first answer choice over here, we're wondering, like, does this one actually work? It looks like everything in both problems originally is the same except for like this. This is the only thing that's different. And unless you think that this 3 with a 3 to the second power is the same thing as 2 to the third power, if they're the same, then this is true. But this is equal to 9 and this is equal to 8. So this one simply cannot be true, right? So I'm just going to go ahead and strike this one out and be like, this is definitely not one of the answer choices. Okay, so that's a quick one to kind of identify right off the bat. And let's take a look at the other ones now. The second and third one, I'm not too sure right now, but if I'm like taking a look at this fourth one, this one kind of stands out to me because it looks very similar to the original one as well. This matches with this. There's a minus sign, there's a minus sign. This all matches as well. The only thing different is this 20.8. So I'm wondering like why this is here, right? And so if you're wondering and you're looking at this 20.8, you should also look here and be like, how, like what changed from here to here? And it looks like somehow they've added 13.8 plus 7. That does equal 20.8, right? And well, first of all, it's division, and then also you can't just go through the parentheses, right? You'd have to go and follow the order. So this is definitely not right because they've broken the order of operations and they didn't even divide, they added instead. So that doesn't make sense. The next one I kind of notice here is taking a look at the last answer choice down here. And so the reason why this one kind of stands out to me is because if you go ahead and follow the order of operations and you just like add these two together, that's going to be 102.4, which this 102.4 definitely matches over here. So that looks kind of promising. Then in the next group of parentheses, you have this like 8 times 3, that's 24. 24 plus 13.8, that's going to end up equaling 37.8. But then you still have to multiply that by 7. So something's a little fishy here, right? So this times 7 is just kind of strange because this has divided by 7, right? So I know there's a lot going on, but this looks very similar. So this 102.4, that's all cool. That's all good to go. And then you end up, I think, getting the same thing over here, but this is just times 7 and this is divided by 7. So that doesn't make any sense. So I'm going to go ahead and scratch this last one as well. That one doesn't work. The next one that stands out to me is this 102.4, this third one. We're kind of wondering, like, does this one work? This 102.4 does match this, so I do like that. And then let's see what's inside this next part. So 6 squared right here, that's 36. 36 plus 1.8, that's going to be 37.8. And then we're going to have to divide it by 7. So let's check to see the original problem. Well, what's 2 to the third power? That's 2 times 2 times 2, that's 8. 8 times 3, that's 24. And 24 plus 13.8, that does equal 37.8. So this whole thing ends up being 37.8. Well, if that's the case, this matches with this. We're subtracting. This whole thing is equivalent to this thing. They're both 37.8, and then they're both dividing by 7. So I think we have a winner here. This one is good. But let's check this second answer choice. So if we were to solve this first parentheses, we'd have to start with the exponent. So 10 squared is going to be 100, but then 100 plus 2.4 is going to be 102.4, which that matches here. So I'm a fan of that. And then what has to happen next? It's going to be 37, it's going to be this 37.8 divided by 7, which is what we had here, and we also had here. So if you needed to write it out in more detail, then absolutely go ahead. But if that made sense, then wonderful. But these are the two that we were wondering about that do end up working. Okay, so these are the two expressions that are equivalent. Feel free to solve all of them if you want to, but hopefully you could see the thought process behind how you can narrow it down a little bit. So hopefully this was helpful in helping strengthen your understanding of order of operations and exponents. And as always, keep up the great work. And hopefully keep on practicing and keep on getting better. All right, so I'll see you later.